students coming in a moment. So let me first say that I'm going to drop back to do the QCD, the running of the QCD coupling constant. And basically, it was to write the Lagrangian, or at least a part of the Lagrangian, that, or the action density that refers to the quark-gluon interactions as we were writing it in the dimensional regularization procedure Z1, and then an AA mu psi bar I gamma mu PAIJ psi j. And so these would be, J would go from 1 to 3 over the 3 colors of the ball. We're just considering one flavor at the moment. And Schwartz's trick was to rewrite this as 4 minus d over 2 G Z1 over Z2 square root of Z3 AA0 mu psi bar 0 I gamma mu TA ij psi 0j. So the idea is to write everything in terms of the fields that are that don't refer to any scale and haven't been renormalized, and these are all the ones with infinite interactions and so forth. And so what we've got here effectively is G0 AA0 mu psi bar 0 I gamma mu TAIJ psi 0j. So that's what we're talking about. So this is the Lagrangian that one finds in the sands of Egypt. Okay. So when we write it in terms of normalized fields, we have this. So let me repeat.
I'm sorry.
What was found on the Rosetta Stone in Egypt was this.
Okay.
On the other hand, if we renormalize at some scale mu, then we have these renormalization constants and these fields here, or equivalently we could write it this way. But comparing these two shows that G0 is effectively this thing. So G0 is GZ1 over Z2 square root Z3 mu to the 4 minus d over 2, which is about 0.05.
Okay.
Oh,
yeah.
Oh.
4 minus d over 2.
yeah. Okay. And the idea is that G0 must be mu independent, so we can write d by d mu of G0 equals 0. So that means that we have 0 is equal to mu d by d mu of the right-hand side, which is G Z1 over Z2 square root Z3 mu to the 4 minus d over 2. Okay. So that's our basic equation, and now what we have to do is interpret this perturbatively, and I don't know, I'm always thinking of these z's as being either 0 or infinity. On the other hand, if we think in terms of dimensional regularization with d to the 3.9, things are not so bad. Close enough. 3.9 is close enough to 4 for government work. so the z's are, each of the z's take this form, like, let me use this. Zi is 1 plus some delta I, and we're imagining that the delta I is maybe 10 or something, 1 over epsilon, something like that. And or 1 over 10, I'm not sure, yeah, maybe 1 over 10 actually. Okay, so the other thing is that we're trying to do this perturbatively, and so what we're going to do is we're going to say that to lowest order, all the z's are 1, and we have g mu to the 4 minus d over 2. So to lowest order, what we have in this expression here is g0 is g mu to the 4 minus d over 2, to lowest order. So I get 2 de Blasius. All right, so to lowest order in the coupling constant. And now, yeah, I think now I'll skip to my other notes. So if we write this way, then we see that g to lowest order is mu to the minus epsilon over 2 g0. Epsilon, of course, is 4 minus d. So this thing is g mu to the epsilon over 2. And so writing things the other way, we have that. And so that means that dg d mu is minus epsilon over 2 mu to the minus epsilon over 2 minus 1 times g0. And now what we've got here is mu d by d mu, so we want to rewrite that. Mu d by d mu is equal to mu dg d mu ddg, and we have dg d mu is that, and so this is equal to minus epsilon over 2 mu to the minus epsilon over 2 minus 1 g0 ddg. And now rewriting that, that's minus epsilon over 2 mu to the minus epsilon over 2 g0 ddg. On the other hand, mu to the minus epsilon over 2 g0, which is what we have here, that's just g. And so what we get is that this thing is actually minus epsilon over 2 g ddg. So mu d mu is minus epsilon over 2 g ddg. That's this equals that. So now we can take, we can rewrite this equation, which of course will form something equals 0. We can rewrite it, and what we get. First of all, what is beta of g? Let me define beta of g for you. So we're going to define beta of g as mu dd mu of g. And why? That's just a definition. And now what we see is we have in this equation what we have is, well, I skipped a few steps here. That equation would be 0 equals mu dd mu of G times all this stuff, which is Z1 over Z2 square root Z3 mu to the epsilon over 2. So I'm letting that equal G. We've got all this stuff. And then we have G mu d mu on the rest of the thing. And plus G mu d d mu on all this other stuff, which is Z1 over Z2 square root Z3 mu to the epsilon mu to the epsilon over 2. Okay. And this is beta of G. And so what's going to happen then is we're going to expand everything in terms of, write them as 1 plus deltas and so forth. And I'm just a little concerned here. Yeah, okay. So what we have is beta of G, which is equal to mu dd mu of G, is then equal to minus, and if I write everything down, even though I'm going to cancel a lot of this stuff, so I'm dividing by that minus sign, and then what we have is G mu d mu of all this Z1 over Z2 mu to the epsilon over 2 square root of Z3. Okay, and so the easiest term is d by d mu on this, and that just gives us an epsilon over 2. Mu to the minus 1, the mu cancels that, and so the first term on the right here is minus epsilon over 2g, because of course everything else cancels. And doing the rest of the terms, if we now substitute what we would have, what would we have? We would have, we can forget about this term and that term, so then we just have 1 plus delta 2 square root 1 plus delta 3 over 1 plus delta 1, and the mu to the epsilon over 2's cancel. We get G mu dd mu of what's left here, which is 1 plus delta 1 over 1 plus delta 2 square root of 1 plus delta 3. And now we're imagining that these deltas somehow are just of the order of 1 plus something like 1 over 10, in as much as epsilon is 0.1. This is, I don't really like this stuff, but I'm doing it because it's a party line. Okay, now, in as much as these deltas are small, we can expand this, and then what we get is that beta of G is minus epsilon over 2G, and the rest of it is what? Well, the lowest order, this is just 1. And, or equivalently, we can cancel the extra terms there, and the rest of it is G, mu d mu. And now what we have here is delta 1, or if you want, let me do it more accurately. What we have is 1 plus delta 1 minus delta 2 minus delta 3 over 2. So that's expanding. 1 over 1 plus delta 2 is 1 minus delta 2. This is 1 plus delta 3 over 2. So it's 1 minus delta 3 over 2, like that. And then we know that mu d mu, so this is equal to minus epsilon over 2g, and then this is minus g. Mu d mu is minus epsilon over 2. So this, in other words, over here somewhere, mu d d mu is minus epsilon over 2g d dg. So we have g, and then minus epsilon over 2 g d dg of all this, mu 1 plus delta 1 minus delta 2 minus delta 3 over 2. And so altogether then beta of g is minus epsilon over 2g plus epsilon. What is that epsilon over 2 doing there? I'm a little concerned. G squared ddg of 1 plus delta 1 minus delta 2 minus delta 3 over 2. I don't want this. Oh, right. So the epsilon is going to go away in a moment. Okay. So I'm not worried about that epsilon. All right. Now let's figure out what these things actually are. The delta 1 and delta 2 and so forth. These quantities in here, so apart from the epsilon over 2g squared and the d by dg, the rest of this is of the following form: minus epsilon over 2g plus epsilon over 2g squared d dg. And all of this is, first of all, a factor of 1 over epsilon, g squared over 16 pi squared. And the rest of this is minus 2 c sub f. These are Casimir's, and I'll evaluate them in just a second. I don't know why we bother to write them as Casimir's. I think it's quarks as a fondness for buzzwords. 4 over 3 n sub f t sub f. Okay, I think I've got everything. All right. Now, obviously, many of these things cancel, and so what we get is beta of g is minus epsilon over 2 g plus the epsilons cancel, so we get a half times 2g cubed over 16 pi squared. So we've altogether got, well, the d by dg is going to hit the g squared. These, of course, are just numbers, so d by dg just gives us a 2g here. The epsilons cancel. And what we have is this, and the rest of this structure here is minus 11 over 3 Ca plus 4 over 3 number of fermion flavors times T sub F. And let me get rid of these notes. Okay, well, what is Ca? Ca is just the number of colors, 3, And T sub F is the normalization factor for the generators in the fundamental representation, F being fundamental. So altogether, this beta of G then is minus epsilon over 2G minus G cubed over 16 pi squared, 11 minus 2/3 NF. And in the trade, one then says beta of G is minus epsilon over 2G minus G cubed over 16 pi squared, and this thing is called beta 0. Beta 0 just being what's in the parentheses here, namely 11 minus 2/3 times the number of flavors. So the number of flavors, of course, is 6 as far as we know. Up, down, charm, strange, top, bottom. And once again, by definition, this is simply mu, dd mu of G. Now we're going to evaluate this equation once we've gotten finally to this equation. We're going to evaluate it in 4 dimensions, which means epsilon goes from 1/10 to 0, in which case we have a simpler equation. We simply have that beta of G now is just simply minus G cubed over 16 pi squared beta 0, and this is equal to mu d mu of G. Now, what we're going to do now is we're going to switch from G to alpha. And what's alpha? Well, alpha, strong, but I'm just going to write it as alpha, is G squared over 4 pi. It's like E squared over pi being the spine structure. Okay, so what we're going to have here is, let's look at mu dd mu of alpha. Well, this is mu dd mu of G squared over 4 pi. So this is mu dg d mu times 2g over 4 pi. So altogether it's just mu g over 2 pi dg d mu, and mu dg d mu is this thing here, so this is equal to, or let me, yeah, that's equal to that, so this is g over 2 pi mu dg d mu, which is mu dg d mu is beta of G, and that is equal to minus G cubed over 16 pi squared, this constant beta 0 that I'm just going to call beta 0, of course. And so now what we've got is mu d alpha d mu is equal to, and I've set epsilon equal to 0. I've got a G cubed here. The point is that it's G over 2 pi times mu dg d mu. So this is G over 2 pi, and so this is G to the 4th over 2 pi like that. Now if we absorb the 4 pi's, what we see is that this is equal to minus beta 0 over 2 pi times G squared over 4 pi squared. So the g to the fourth or right, 2 pi is here, 4 pi is 16 pi squared. So this is our equation then. In other words, it's mu d alpha d mu is equal to minus beta 0 over 2 pi alpha squared. So that's the equation that we want to integrate at epsilon equal to 0. And of course, we've blocked out this is a first order differential equation. We can always solve first order differential equations. And so what we do is we say minus d alpha over alpha squared is beta 0 over 2 pi d mu over mu. We integrate that and we get 1 over alpha minus 1 over alpha 0 equals beta 0 over 2 pi natural log of mu over mu 0. This tells us that 1 over alpha is equal to 1 over alpha 0 plus beta 0 over 2 pi log mu over mu 0. And this tells us then that alpha is 1 over all of this, which is 1 over alpha 0 plus beta 0 over 2 pi log mu over mu 0. Or equivalently, alpha is alpha 0 divided by 1 plus alpha 0 beta 0 over 2 pi log mu over mu 0. And now just another step or so is let me see, did I do this correctly? Yeah, all right. Actually, it was better to leave it like this. So let me go back to this form. 1 over alpha 0 plus beta 0 over 2 pi log mu minus log mu 0. Okay. All right, what are we going to do? We're going to set log mu 0 equal to log of something we'll call lambda QCD plus 2 pi over beta 0 alpha 0. So when we do that, what happens? This gives us alpha is 1 over alpha 0 plus beta 0 over 2 pi log mu minus log lambda minus 2 pi over beta 0 alpha 0. And this then, this last term was chosen so that when multiplied by beta 0 over 2 pi, cancels the leading term there. And what's left then is the log of mu over lambda. And so this is 1 over beta 0 over 2 pi log mu over lambda. So that's the lowest order running strong interaction coupling constant, alpha s. It's 1 over beta 0 over 2 pi. And maybe to write it one more time, it's alpha s is 1 over. Now beta 0, just remember, that's 11 minus 2/3 NF. All of that divided by 2 pi times log mu over lambda QCD. Okay. So the running coupling constant decreases as lambda goes to infinity, it decreases logarithmically like an inverse log. I suppose the nicer way to write this is 2 pi over 11 minus 2/3 the fermions log mu over lambda cubed. So that's a nice way of writing it. So this is asymptotic freedom. I think that was, I imagine it was Sidney Coleman's term, because of all the people who were working in this area, he was the one who really had a way with words. And so the idea is that as mu goes to infinity, the coupling goes to 0, and you can use perturbation theory. On the other hand, as mu goes to 0, well, you no longer can use perturbation theory, but if you could, you'd say that strong interaction coupling constant is very, very strong. And that's why things are confined. And that's called infrared slavery. So mu to infinity is that. Mu to 0 is infrared slavery. And that's again, I imagine, Sidney Coleman's. All right, so that's the end of the spiel about QCD, running coupling constant, that I forgot to do last time. So instead now we want to turn back to or resume our discussion of symmetries, and there can be explicit or broken, and if they're broken, they can be spontaneously broken or explicitly broken. And the basic idea is if you have a nice Lagrangian or a nice action, it has symmetry, and so if, on the other hand, the ground state isn't unique, but instead under the symmetry moves around a symmetrical set of vacua that all have the same energy, of course, then you say the symmetry is spontaneously broken. And just to review some of this, because it's so important, and also let's remember the symmetries we're talking about are exact for the Hamilton, for the action, for the Lagrangian. And then, but we're talking global at first. We'll go to local next Tuesday. But right now, let's do global, and let's repeat Emmy Lothar's theorem, namely that if this is a symmetry, then we have partial L, partial phi I, partial alpha A. I'm imagining that we have generators TA for each of these symmetries, and then this is partial L, partial the muth derivative of phi I, and then that's the same thing as d mu of partial phi I, partial alpha A. And then, so this is because it's a global, it's an exact global symmetry, because if we now enforce the equations of motion, we can write partial L, partial phi I as the muth derivative of partial L, partial phi I, the muth derivative of phi I, and then this is partial phi I, partial alpha A, and then the other term is partial L, partial phi I comma mu, d mu of partial phi I, partial alpha A. And that then is zero if the equations of motion are satisfied. This thing is a total derivative, so this is d mu of j mu, that's a mu. Sorry. J mu A. And we say J mu A then is partial L, partial phi, I comma mu, partial phi I, partial alpha A. And of course what we're talking about here is that phi I prime is phi I plus I TA ij alpha A phi j. So this is for small transformations. And at this point, since I've written things in terms of I and T's, I'm thinking of these, I guess, as complex fields. Otherwise, one thinks of them as real fields, and then this would be an infinitesimal orthogonal transformation of the real fields. Anyway, in this case, what we have here is partial L, partial phi I comma mu, and then we would have I TA ij phi j. So this would be the eighth current. So for each generator of the symmetry, we have a conserved current JA, and there'd be a conserved charge QA, which would be an integral J0A d cubed x. These charges would be conserved. They would commute with the Hamiltonian. And if we now look at what happens here, if mu is 0, you see this is the derivative of the action density with respect to the time derivatives of the field. But that's the ith conjugate momentum. So J0 A is actually pi I. And I guess we've got this I here. TAIJ phi j. So the current density is the conjugate momentum TA ij phi j. And while we're talking about it, let's just look at what's going on here. The commutator of the charge with respect to, say, the kth field at y, this would be an integral of J0A commutator phi k of y d cubed x, where this is x. So this would be an integral of the commutator of I, pi I of x, TAIJ phi j of x, all that with phi k of y d cubed x. And we can imagine that this is an equal time commutator, because after all, we can, whatever the time ty is, we can choose the time independent charge to be at that time, because it's time independent. And so then we have the canonical commutation relation, namely pi I of x and t, phi k of y and t is minus I delta. Minus I delta cubed of x minus y. The I times the minus I is just 1, and we have delta ik, because the I and the k have to match. So this is delta ik delta cubed x minus y ta ij phi j of x d cubed x, well, the delta function shows us what this is. Namely, this is just ta k j phi j of y. So the commutator of phi k of y with qa is the generator acting on the vector of fields phi j. Okay. All right, so last time what we learned was that when the Q's, which is to say these guys, how shall I say, when they were eigenvectors of the mass matrix with eigenvalue 0, then they corresponded to Goldstone bosons or massless particles, just as long as this linear combination wasn't 0. But there are, of course, cases where it's 0, where the t's on the phi's are 0. In the language of the Q's, what we have is that if we have QA on the ground state equal to 0, then this QA generates a symmetry, that's unbroken. On the other hand, if QA on the vacuum is not 0, then we have something that's spontaneously broken. And we can see this, another way of seeing this is to say, suppose E0 on the vacuum is H on the vacuum. That is to say, the energy of the ground state is E0. Well, then the Hamiltonian action on QA on 0 is the same thing as QA Hamiltonian acting on 0. That's E0 QA on 0. So that means that this state QA on 0 is a state that has the same energy as the vacuum. On the other hand, it's also a state that's translationally invariant because there isn't any x here. So that's a state of momentum 0. So you have a state of momentum 0 and energy 0 that's not the vacuum, but rather something else, QA on the vacuum. That's the Goldstone particle at rest. It has mass 0, so it has energy 0. We can make something that has finite momentum, and the way we do that is we say, well, let pi sub a of 0, we're saying that is, and Schwartz uses this lingo here, minus 2I over f QA on the ground state. And so then we take pi a with some finite momentum minus 2I over f. This thing here, of course, is minus 2I over f integral j0 of x d cubed x, because that's what q0 is. Okay. We want to make a state of finite momentum. Instead of having 1, we have e to the I px. Okay. So this thing is integral d cubed x. And I don't guarantee plus or minus signs here. So this is a state of momentum p. On the other hand, as p goes to 0, this thing goes to that, and the energy of whatever it is goes to E0, so this is a state of momentum, of energy, of a massless state. So we have a massless, we have a zero mass particle for every generator of a symmetry of the action that does not annihilate, whose charge does not annihilate the vacuum. Okay. So QA Goldstone boson, i.e. m equals 0. Okay. Now, Schwartz goes through some stuff about effective field theories, and in particular a linear sigma model. I guess I'll go through it. Probably useful. L is d mu phi star, d mu phi, plus m squared phi star phi minus lambda over 4 phi star phi squared. Okay, so this is a case where you've got, this is what I called last time example 2. It's U1, and the mass term has the wrong sign, so phi equals 0, which would be a symmetric vacuum, is not the ground state. The ground state is a circle. And in particular, the possible ground states 0 comma theta, phi, 0 comma theta are just square root of 2m squared over lambda e to the I theta. So there's an infinite number of them. It's a symmetric state of asymmetric vacuum. Schwartz likes to use this kind of this notation, which I find a little bit. I think it's confusing, but I did the clear thing for you on Tuesday, so I'm going to do the confusing thing now. This is e to the I pi of x over f pi. F pi is just a number. And so we're going to write the complex field this way. As I said, the simple way to write the complex field is just 1 over root 2 x plus I y. I mean phi 1 plus I phi 2. And then if your vacuum is here, you pick phi 1 to be the one that goes this way. And so it has mass because it bumps up against the curvature of the Mexican hat. On the other hand, phi 2 is the Goldstone because it moves in the direction where it's flat. But another way of doing it is to write it this way. And if we then expand this, if we use this parametrization of the complex field phi, then the action density L is a half d mu sigma plus this square root of 2m squared over lambda plus sigma over root 2 squared 1 over f pi squared. So we're expanding this thing now. And it's d mu pi d mu pi, and then other terms are minus m to the 4th over lambda plus m squared sigma squared plus square root of lambda over 2 m sigma cubed plus lambda sigma 4th over 16. Okay, so that's what we've got, and Schwartz sets f pi equal to 2m over square root of lambda or square root of 2v. And if we do that, then we get the right normalization for pi. In other words, here's the pi field, and that's the normalization, and so we want the right normalization there. So pi, you see sigma has a mass term sitting right there, and the mass term has the right sign, namely negative. But pi has gradients, but there's no pi term there. So pi is massless. So this is the Goldstone. And the reason why we call it pi and risk confusion with conjugate momentum is that the pion is light. And one of the puzzles of the early days of nuclear physics and strong interaction physics was how come the pion has a mass of 140 or so MeV, whereas the neutron and the proton are 1,000 MeV? It's a factor of 7 or so. And the other mesons then with a K was over 500 MeV, or around 500 MeV. And then the other baryons were heavier than the neutron and the proton. So the puzzle was why are the pions so light? Actually, I don't think they're all that light. A factor of 7 is not a factor of 1 over 100. But anyway, the idea then is that the pion, that in the limit in which the pion is massless, it's a Goldstone boson of some effective field theory. So that's the way many people look at this. Now, the action, of course, is invariant under a certain transformation. Namely, if we send pi to pi plus something, well, it cancels. It just changes the phase. That's the U1 transformation that is a symmetry of the action, but not of the vacuum. And so L is invariant under pi goes to pi plus, say, f pi times theta. And so now, what, for some reason, well, Schwartz considers a limit where we set m and lambda going to infinity, but in such a way that f pi stays constant. And in that limit, this L goes to L0, which is a half d mu pi, d mu pi. In other words, that's just a theory with a single Goldstone that's perfectly massless. All right, this is called the nonlinear sigma model. Whereas this thing is called the linear sigma model. Anyway, it's just this terminology. I suppose it's better than what is in the astronomical terminology, but not all that much better. J mu is partial L, partial pi comma mu, partial pi, partial theta, and that is then f pi d mu pi. And let's see, we had a J mu back over here. We had J0 being what gives you pi, and so we can consider this matrix element J mu of 0 on pi of the momentum state here, and actually this would be an X actually, so let me change it. And what's this? Well, that is 0 f pi d mu pi on 0. Not on 0, on a pi of p. And, well, we can pull out the derivative and the f pi, so we get f pi d mu. And now we have 0 pi of x so this is the pi field, this is the pi state of momentum p. And on the other hand, pi of x, it's generally true that this thing, again, we've got Schwarz's metric and so forth to deal with. Let me just say that this is e to the I px pi of 0 e to the minus I px pi of p. Okay. These p's are momentum, four momentum operators, Hamiltonian and momentum. They generate translations. This is a unitary operator. This takes pi of 0 to pi of x. On the other hand, the vacuum is an eigenstate of the form of p mu with eigenvalue 0 because it has no energy or momentum. Well, we're talking about E0, but let's just imagine that we've changed E. We're not doing dark energy here, so let's set E0 to 0. In that case, this guy is 0 acting on here. But this one is not. This gives us a P. And so altogether then, we get that this thing is equal to I P mu F pi times 0 pi of 0 pi of P. And so this is equal to, in other words, J mu is P mu F pi times the matrix element. Pi P is the Goldstone boson. Okay, so I frankly don't find these sections all that clear. But anyway, it's just a more these arguments with effective quantum field theory are more abstract and more confusing, whereas what's much more concrete is what I did on Tuesday, where we had an explicit action with an explicit symmetry, and then we could tell whether the vacuum was unique or not, and so forth, and much clearer. All right, now we're going to switch to QCD, and we don't have much blackboard or time, but I think we have more time than blackboard, actually. So let's write L as, what is it, minus a quarter, FA mu nu, FA mu nu, and then it's plus I U bar, P slash U, plus I D bar, P slash D, minus MU, U bar U, minus MD, U bar D. Okay, so this is just, this is QCD with two flavors, NF equal to 2. The F is the A goes from 1 to 8. Inside here we have the gluons and so forth. Now, for practical purposes, these guys are very small on the scale of lambda QCD. So we can learn something by taking the limit in which the quark masses vanish. And in fact, let me just remind you that Gribov actually thought that and he may in fact be right, or have been right. The lightness of the up and down quarks had a lot to do with confinement. In any event, let's set those terms equal to 0. Well, if we do, use the magic of an eraser, we have this expression. And now, what we notice is that we've got extra symmetry, having set them equal to 0, because we can decompose, we can insert in here and in there, we can insert 1 plus gamma 5, 1 minus gamma 5, for example. And what is this? Well, this is equal to 1 minus gamma 5 squared, period. Gamma 5 squared is minus 1, and at least in these units. And so this thing altogether is 2. So this is just a multiple of the identity matrix. On the other hand, gamma 5 completely commutes with the gammas here. So if we insert both of these guys here, then we're just, well, divide by root 2, say, and then we get just the identity. We can pull, say, 1 plus gamma 5 over, then it becomes 1 minus gamma 5. And then what we've got is, we've got d dagger gamma 0, 1 minus gamma 5, and then d slash, so let me see, we had 1 minus gamma 5, right? It was a 1 plus, then became a 1 minus. Now, if we pull it through there, we get gamma 0, it's again 1 plus, and this thing is actually 1 minus gamma 5 d adjoint. Because I think gamma 5 is anti-Hermitian. Okay. All right. In any event, what we can do is we can define d left-right as 1 minus or plus gamma 5 over 2 times d. D, of course, is a 4 Dirac spinner. And gamma 5 in reasonable units is such that 1 minus gamma 5 over 2 looks like this. 1, 0, 0, 0, where each of these are 2 by 2. And 1 plus gamma 5 has a 0 here and a 1 there. So, doing all this shenanigans, what we wind up with is that we can write lambda QCD as minus a quarter, and I'll just call it f squared. And then the rest of it is we can write it this way, u bar left, d slash u left, plus u bar right, d slash u right, plus d bar left, d slash d left, plus d bar right, d slash d right. So we decompose it this way. This is exactly the same as the original thing. Now what we notice is we've got 2 U2 symmetries, global. Namely, we can rotate UL and DL into each other globally, and U right and D right into each other. Notice that this is because the structure, if you can rotate flavors as long as you keep left and right together. You don't want to rotate right into left without compensating for that.
Okay.
Now, maybe one can have an interesting theory compensating, but we're not doing that now. Okay, so this is something that has U2 cross U2. In fact, we can call it U2 left cross U2 right, global symmetry. Okay. And of course, U2 is U1 cross SU2. Now, U1s are problems. U1 symmetries often have something called anomalies. And anomalies frighten people. And so we're going to avoid talking about anomalies until the weather gets warm enough so that we don't care. Schwartz postpones it, I don't know, chapter 29 or 34 or something. And he's quite right to do that. Okay, anyway. So we're just going to look at an SU2 left cross SU2 right. We've got those symmetries. And these symmetries then are, they're actually broken by explicitly by the masses of the up and down quarks. But if we ignore those masses, then we have an exact symmetry of the action. On the other hand, we can have a somewhat better symmetry if we say, well, okay, the U and D quarks aren't don't have zero masses, but they have similar masses, and the masses, they have similar masses, small masses, and so if we imagine those masses were the same, then we would have some. That blackboard is just awful. All right, let me write here because we have a little bit of black type. We can just write this as M U bar U plus D bar D. So now we have something that is invariant under an SU2 in which we do the left and the right simultaneously. That's still an exact symmetry in the limit that the up and down quarks have the same mass. And okay, what seems to be true is that because, now we don't understand QCD because it's a strongly interacting, non-abelian gauge theory, and I mean, we can't even do strongly interacting any I mean, unless it's a free theory. And but what seems to be the case is that in the ground state of QCD, U bar U plus D bar D is not zero, and in fact, we can set it equal to VQ. For some reason, Schwartz screwed up, and he thinks that U bar U has a mean value. It's actually U bar U plus D bar D that have a mean value, not, and that means the sum of the two then is invariant under the isospin SU2. All right, so let's, on the other hand, I guess if the sum of the two is non-zero, then each of them has to be non-zero, doesn't it? In any event, the thing that's invariant under when you require that the SU2 left and SU2 right be the same global symmetry, that's called isospin. And this mean value is isospin invariant, whereas the individual ones aren't.
What do you call the U1s that you took out of there?
Excuse me?
What do you call the U1s that you took out? So you're calling the SU2 the isospin?
Well, God, I don't know. one of the U1s is, really does have an anomaly that we don't like. On the other hand, another U1 can be sort of resuscitated as B minus L, baryon number minus lepton number, and that's not anomalous. All right, I think any more questions? Let's see, you just asked a question.